Hello, my name is William and I am a PhD researcher from Catholique University of Louvain in Belgium, working on polyfunctional thiols. Ever heard about it? Polyfunctional thiols are molecules containing one thiol function and 3 carbons apart another function, which can be an aldehyde, a ketone, an ester, or an alcohol. If you like the citrusy and tropical fruit notes in your IPAs, you should be grateful to the thiols responsible for those very pleasant aromas. Thiols present in beer mainly originate from hops. They can be found in their free form, but also in a bound form as a precursors. 2 types of precursors exist: glutathione precursors, which mean one thiol bound to 3 amino acids, and cysteine-related conjugates, one thiol bound to a cysteine amino acid. Those precursors are too heavy to be volatile, so they don't have a direct impact on the beer flavor. However, they represent a huge pool of free thiols, provided that those thiols can be released from the precursors. And this is the main research question of my thesis: how to release free thiols from their precursors in hops. Well, first we have noticed that some chemical release naturally occurs during the brewing process, but this is not the main source of release. The biggest potential for thiol release occurs during fermentation, thanks to an enzymatic process. Indeed, we have identified 2 enzymes able to transform a glutathioneated precursor, a so-called pro-precursor, into the free thiols form via a cysteine-related precursor. In order to understand how and when free thiols are released, we have synthesized some thiol precursors, which we have spiked in an unhopped wort. After 7 days of fermentation at 24 degrees and 3 days of cold maturation, we have extracted thiols from the beer and injected them in GC-PFPD to measure them. We first decided to compare a whole set of lager yeast with one previously studied ale yeast. We see that K97, an ale yeast, has higher release rates from cis conjugates. Surprisingly, the trend is opposite regarding glue conjugates, especially for L7 yeast. We also see that each yeast strain has its own release selectivity according to the nature of the thiol. Next to that, and still with a focus on lager yeast, we try to optimize the fermentation parameters with L7 yeast. Therefore, we launched fermentations at different temperatures and with different fan levels. We observed that by decreasing the temperature from 24 to 12 degrees, we had an increased release of thiols from cis conjugates. On the other hand, we saw no esterification anymore from G conjugates. Nitrogen reduction has as a consequence a higher esterification of alcohols from cis conjugates, but no effect on G conjugates. As it was evidence that the period of cold maturation was necessary to see thiol release when working with ale yeast, we decided to investigate the impact of that cold period on lager yeast as well. We launched several fermentations at 12 degrees during 4 or 7 days, followed for some of them by a maturation with cold or warm temperatures. We first observed that thiols were released in all samples, even those without cold maturation. This suggests that fermentation at 12 degrees is sufficient to observe thiol release. We also see a higher release with 7 days fermentations, leading to the suggestion that a long contact time is required for thiol release. When applying a warm maturation, we see some thiol release, but in lower proportions, suggesting that thiols might be degraded at those temperatures. We can conclude from this experiment that the best conditions for the highest thiol release are long fermentations and a cold maturation. Actually, what brewers knew for decades.